if we want to get the residual values for a set of data all in one shot, because we did it yesterday, the by hand approach. As we know, nothing is really by hand. You can actually create the residual plot using the calculator, and then use that to come up the values that make up that residual plot. Right. So I have the data set from the bicycle question in here. So I'm just going to refer to that just to show you the technique. So first thing you do is you run the regression. I already did it here, but I'll do it again. You run the regression, so you go regression, select the model, linear, it plots the graph, and through I believe a flaw in the coding process for the calculator, you have to go back in. Yeah.
Sorry,
Frozen screen. Oh.
Oh
Yeah, I got it. I always accidentally copy way too many. So, yeah, you got it, bro. All right, so parts. So yeah, you go back into the regression tab, and your equation will be there. My understanding, I think you folks told me yesterday, maybe it was the other class, I don't remember, but it'll give it to you in the correct order with the beta version. Just mine is stuck in the old version, so so just make sure you write it the correct way. A plus bx, right? In terms of free response, I'm pretty lenient with that. As long as you have the hat on the Y, you're good. Right, but on the AP, they're a little bit more strict about that sort of thing. And it's also, if you're just kind of thinking in terms of multiple choice questions, if you structure your equation the correct way, you're more likely to match that with one of the multiple choices. All right. So you go on down the line. You don't even have to look too far to see it. Residual plot. All right. Then you have your prediction stuff. You could also remove the regression if you want. All right. That has value too. But click on or hit OK on residual plot, and it brings up a plot of the residual values. All right, so again, this is referencing this data set here, the cost of mountain bikes. So I actually did this problem with the other class yesterday. If there's any pattern whatsoever in the residual plot, any recognizable pattern, it doesn't have to be perfect, but as long as you can look at it and say, hey, that looks like, and in this case I would say a parabola, that would be my indication that a linear regression is not really appropriate for this data set. Right? Some other model would be more appropriate. Right? So again, it doesn't have to be a perfect fit. It's kind of like looking at the clouds. Yeah, I see an alligator up there. No, I don't see that. You know, like if you have to like will it into existence, I would say there's probably not a pattern there. But if it's something that's like, okay, it's around the right shape of a cubic or a sine function or something like that, then you can claim that there is a pattern, and therefore a linear model would not be appropriate. All right. And so I just threw these notes back on page 8. For this problem, there was a pattern in the residual plot, and that means that it's not appropriate to use a linear model. All right. So I know it's kind of out of order, but it was the data I had in my calculator at the time. So as you know, typing in this data was not the easiest thing in the world. I had to tell like 3 stories. Domino's Pizza. Sure. No. Byron, end of the period. Office. So any pattern means the linear model is not appropriate. Now, you run into the issue of like, okay, well, that's all well and good. Do I just like scrap this whole statistical inferential procedure? You know, like it doesn't work, so I guess I don't have to do any more like analysis. No, it just means that we have to learn other techniques to evaluate a data set. Right? Now, it's weird. I feel like the College Board goes out of their way to sometimes make things more complicated so that they can test you on it without you having the ability to go right into a calculator and get the answer. There is a quadratic regression function built into pretty much all calculators that do statistics. The problem is they want a quadratic transformation, right? Quadratic transformation uses a different method, right? So there is a formula. I mean, you remember seeing it anyway. This disgusting formula for linear regression or linear correlation. There's a equally disgusting formula for quadratic regressions and correlations, right? So, set of formulas anyway. But it's built in. If you need to just get a quick sense of what's going on, you could go into, again, I'll just go back, go into the regression menu and pull up a different model. Like, for example, I think it's quadratic, so I would do that. And you see you have a curve that better fits the data, all right? And you could get the equation from that. Now, when I hit, the R squared value is even a little bit better, right? So, actually a lot better. If you go into the residual plot for the quadratic, now the data points are scattered all over the place, no discernible pattern. So this gives me a sense that a quadratic regression is more appropriate. And again, like I said, quadratic regressions are wonderful things. They want a quadratic transformation, all right? So, and honestly, I think it has to do, I'm just guessing, they don't really get into like their thinking behind why certain things are allowed and other things aren't. I have a suspicion it's because some calculators do higher level regressions and others don't, and they want to keep everything relatively fair, right? Most calculators do a quadratic regression, but when you want like a 6-degree polynomial regression, you know, the higher end calculators will do that. The lower end ones wouldn't. So I suspect it's to keep things fair. All right, and if anybody's going to use a numworks calculator to write a program to do a 6-degree polynomial regression, but more power to them. It's going to take a little while. All right, so residual plots are really useful to determine the appropriateness. Now, what I do is a little bit of a hybrid approach. We know we have to do a quadratic transformation in this case, right? How do I know? Because I ran a quadratic regression, pulled up the residuals, and the residual plot shows no pattern. So now I'm confirming to myself a quadratic method is best, all right, at least in comparison to the linear. So then I look at it and say, okay, well, I have to do a quadratic transformation, but at least I know it's quadratic. Right? I'm not going to go looking for a sine function, because you could have made a case for a sine function. You know, anything that's got a increase-decrease relationship, you don't know what's happening after the fact. Maybe later on, it decreases and then increases again and makes a sine wave, right? Context would be an overriding factor, though. I wouldn't expect that to be the case when dealing with ratings of mountain bikes, but it is, it's possible that if you're talking about temperatures over time, sure. I mean, throughout the year, the temperatures increase, then decrease, and then increase again the following year, decrease, and throughout each year, you get one arch of a sine wave, right? At more extreme weather places, maybe it's a little bit different, but it's generally that trend, right? So any pattern in a residual plot tells us that whatever model you're looking at is not going to be appropriate. So, I mean, I gave some examples of what a scattered residual plot may look like. Then an example of what one with a pattern would look like. This one is, so this is on page 11. This was the one that kind of throws people for a loop, because just because you're not familiar with a function doesn't mean it doesn't exist, right? There is a pattern here. This is a telescopic pattern, right? So you're looking at something that's pretty close to the axis early on, but then it kind of goes off the rails after the fact or down the line, right? You could make a case that it's oscillating, but then not maintaining its amplitude. So with increasing amplitude, and there are functions out there that do that. They're called telescopic functions. All right. So, and there could be hybrid functions or composite functions, as you might know them, that have characteristics of one function and another mixed together. So like a sine function with an exponential, it's going to have aspects of both. So those are some things that it doesn't have to be, just going back to pre-calc or algebra 2, it doesn't have to be like the parent function. Like it doesn't have to behave just like a cubic. It could be a cubic merged with a sine function, right? So that's why we just look for patterns. Do I see a pattern? And then worry about what it maps to in terms of a function later. But outliers and influential points are always going to be a problem. Right? Anything that lies off the beaten path. You know, I always look at outliers as, man, that would be pretty close to being a parabola if it wasn't for that point over there. Right? That's a pretty good way to think about it. Right? Now, an influential point is an outlier in the horizontal direction. An outlier can be use a term in its own definition. So some weird point floating out there in space, but remember, you're working in 2 dimensions. It could be floating high, floating low, or maybe floating east or west. All right. So if it's east or west, then it's going to be an influential point. If it's north-south, then it's going to be just an outlier. All right. So we call that an outlier without influence, but most people just kind of scale it down and say it's an outlier, right? The umbrella topic is outlier. You have outlier without influence, outlier with influence. The influential ones are the ones that are deviant in the east-west direction, all right? Bottom line is the influential points are the ones that would cause the most trouble, all right? Because an outlier in the positive direction, whether it's, in the vertical direction, whether it's positive or negative, is going to be, it's really only going to affect the y-intercept. So let's say you have a bunch of points here, and then you have one outlier over here. Okay? Your line may look something like this. You know, the line that best fits the data. Now, if I remove that, if I remove that outlier, it's not going to impact the slope as much as it's going to impact the y-intercept. Minimal change to the slope, the y-intercept will change. So it'll be just a vertical shift. All right. So you take that high point off, you got a line, it's tending towards it. You think about every point as having magnetic pull on the line itself. So I take that point out, it just drops down a little. All right. Now, as opposed to an influential point, for some reason I decided not to give you any room whatsoever to draw this picture. So that's, you know what that is. I suspect this line was probably, this line of writing was supposed to be on the next page, because that just seems to make sense. And since I never tend to read the stuff that I write contextually, I don't know if that makes sense, but I'm sure it does. All right, so bunch of points here, and then you have one line off the beaten path over in the easterly direction. Your graph is going to look something like this. All right, same graph of points without that influential one. So knock that off. This line is going to snap. Oh, resize. It's going to snap back towards the bulk of the points. All right. Now that might not seem like a big deal. Like, why is it more important for an outlier to be in the horizontal direction versus the vertical one? If you remember how we computed the correlation coefficient, the slope of the regression line, we use the correlation coefficient as a multiplier. So what impacts the correlation coefficient impacts the slope and vice versa. So if I know my slope is going to increase, that means in the positive direction, that means my correlation is going to increase. And correlation increasing is a good thing if you're looking for a relationship between two variables. All right, so this one is an outlier without influence. This one they just call an influential point, but it really is an outlier with influence. All right. And I find that that's the case when it comes to math, but not the function related math. And people come up with like quick shorthand hand way of saying things, and it just confuses the living daylights out of people. Right? So, because it, you know, the original definition and the ones that the College Board uses, and actually most textbooks, they distinguish between an outlier and an influential point, making it seem like they're two completely different things. They're both part of the same category. It's just one has influence, the other doesn't. All right. So I gave an example on the next page. You got all the facts and everything. You know, just the same visual, but I think like the separate diagrams kind of make it feel a little bit better. But the one after that, page 13, pop some data in the calculator. I'm going to show you how to evaluate instances in which there is an outlier or an influential point. Just bearing in mind that an outlier typically is a point that should not be in the data set because usually there's an error involved. You know, like data collection process, you're collecting the ages of students in an elementary school. So you got a student that's 5 years old, a student that's 8 years old, a student that's 10 years old. But then when you put it into a spreadsheet, the 5-year-old and the 8-year-old, for whatever reason, you put in as 58. You know, you forgot to hit enter. So now you have an outlier. Right? That shouldn't be there. That's a mistake. You would go ahead and fix that. Hopefully you wouldn't get to the analysis part without picking up that mistake, but that's part of it. So anyway, type the data in. So 6, oops, 6. You see, I almost did the same thing. Didn't hit enter. 6, 9, 3, 8, 7, 5, and so on. As the course goes on, when it comes to completing projects, the amount of rigor that I'll be expecting in the completion of those projects will increase accordingly, because there's a lot of like fine details now. You know, so when we talk about the next project, I'll give you the overview and the rubric and all that. But there's a lot going on between units 3 and units 3 and 4. So if you haven't started reading unit 3 yet, make sure you do that, because this, even though this is a huge thick packet, we're already maybe not halfway through, but like a third of the way through it. We're only like a couple days in. So yeah, it goes by quick. And most of the concepts here you'll find to be fairly easy, but once we get to transformations, you'd have to know something about the functions you're working with, because, you know, working with logarithms, for example, if you haven't looked at that in a while, you might have to brush up a little bit. All right, so draw a scatter plot. I'll save you from that. Just graph it. Do this. Now, looking at this graph, I'll bring it in closer. You could definitely see that there's some points off the beaten path. But in theory, you should probably see that in the data too. When you're given a graph, that's one thing, but when you actually have to type the data in, you should really consider what is being put into your calculator. It's like, whoa, that number's pretty big in comparison to what we just did. Like, for example, when I'm typing in the X scores, I'm looking at it like, oh, one digit number, one digit number, one digit number. Oh, 20 all of a sudden? That might be a little big. All right. Maybe not as clear for the second column, but you know, you just kind of keep an eye on things. I suspect that this is an outlier without influence. and this is an outlier with influence. Okay, I'm just going to move this over because it doesn't look like I have an eye there. All right, so outlier without influence and outlier with influence. Now, first thing they're asking us to do is, aside from the scatter plot, determine if there's a pattern. Does it appear to be positive, negatively correlated? Well, you consider it mentally as if the outliers aren't there. It looks like I can get a line through this, sure, but it looks like I can probably get some sort of polynomial through that, right? So, but either way, it does seem to have a positive relationship. It does seem to be on the upswing, right? So it looks like a positive relationship, and I'm going to say possibly linear. And this is the thing that people who just kind of gloss over the content, they'll miss out on. But if you're careful and you really think it through, yes, I could make a polynomial that goes through that. It might be a cubic function. It could be part of an oscillating function. I'm not really sure. But the tie goes to the linear function. All right? So if the correlation values are in the same neighborhood and the residual plot bears it out, default to the linear function because that's always going to be a simpler one. All right? So positively, negatively correlated, make the call on that. Explanatory response, that requires us to read the question, I guess. The explanatory. Right, we'd have an aptitude test and then productivity at work. All right, well, I'd like to think that if there's a test related to the aptitude of an individual associated with this particular job, that should lead to productivity at work. I mean, I don't know if it'll cause it, and there's flaws everywhere, but I would think that you would not measure a person's aptitude after they've already demonstrated that they can do the work. Hey, how good will you be at doing the work? Well, I just showed you like last week. I was great. Right? I guess you can make a case for, let's say, a person who's not doing so well at work. It's like, do you even know what you're doing? Like, is this job right for you? Why don't you take this aptitude test here and we'll see. I mean, that's a flawed approach too, because you would have just like emotionally crippled that individual. So they're probably not going to perform as well on the aptitude test. But yeah, that's the only way I could justify kind of going the other way. All right, regression. You can pull the line. We need that anyway. They asked for the R value, and in the regression tab here, they only give you the R squared, but I mean that R squared isn't really lighting the world on fire one way or the other. But if you want to get just the R without having to do the extra computation, then go into the stats menu, right? But let me just get the plot here. Y hat is equal to 20. Poor quality hat. 25.844 plus 1.546x. Sketch it onto the graph, easy enough. I mean, assuming that you actually made the graph, but I'll just overwrite it here. I don't know if it's a coincidence that it went through the target value. My suspicion is that that's related to the X bar and the Y bar, that particular point, and so that should be on the line. So I'm kind of surprised that came up before I did any calculations, right? So I don't know if it like if you go into a graph, a scatter plot, will it automatically target the mean value? If it does, that's kind of cool. All right. So anyway, I'm going to go into, like I said, the stats menu to come up with the R value. So 0.444, R is equal to 0.444. Now, does it support your answer to A? Well, yeah. Oh, I know. Oh, I did say positive. So I'm just going to say yes and highlight the thing that I think it supports, that it's positive and possibly a linear relationship. All right, I didn't get pinned down on my claim here. I didn't say, oh yeah, it's a strong positive linear correlation. Well then, no, it doesn't support it, right? But positive, possibly linear, I think it supports that. All right. Discuss any outliers or influential points by visually looking at the scatter plot. That's a little redundant. Visually looking. Suppose visually doesn't need to be there. I don't know how else you'd look at it. So yeah, it appears that this point and this point. So the one in the neighborhood of the x value of 8, so that would be 870. We've already marked these on the graph, so that should be good enough. And then 2040. The 870 and the 2040. They found me. All right. So again, outlier without influence. That's what we suspect. Outlier with influence. All right, so now what we have to do, and by the way, anytime you analyze any question that involves correlation and regression, you got to do all of this stuff, even if it doesn't ask you. And I'll tell you, definitely on the AP, it's not going to ask you. I haven't decided whether I'm going to spell it out for you on the test. All right. So for the removal of influential points and all that stuff, we want to go into our data set. We want to go into our data set and first make a copy of the values that we have, all right? Because we need, and this is just a general rule of thumb, and it's always going to play out this way. You're going to need the original data set and also the one where we remove outliers, all right? So make a copy, fill with formula. Folks, I know this stuff is easy, but I still think it requires a little bit of focus and attentiveness. So fill with formula. It's also possible it's not as easy as you think it is, so we'll see. Because we still haven't gotten to the part where we actually analyze stuff. It's just crunching numbers, not even. Right? So I'm going to still work off my x1, y1. We do not remove multiple outliers simultaneously. All right? You might suspect that there's 3 or 4 outliers. You remove them one at a time, which can be incredibly frustrating. That being said, if you only have like 10 data points and you're removing like 4 of them that you suspect are outliers, well, guess what? They're not outliers. Right? Because if you have to remove half the data set in order to find a pattern, there's no pattern there. All right? So one at a time, we remove them. So, and you have to itemize it. You have to look at it and say, all right, so this is what I'm going to do. I'm going to remove 870 and see what happens. Now, the things that could happen would be a change in the regression, specifically either a substantial significant, either a change in the y-intercept or a change in the slope. The change in the slope is the more important, right? In the long run, that has more of an effect on the nature of the function, right? So I'm going to take out the 870, and then I'm going to recompute Fortunately, recomputing just means do the same thing we did before. So now, I got to put the right graph on. I want my red graph here. So I got to turn these points off. These are the ones I saved. So let's show in graph, turn that off. All right. I'm not sure why I just showed the blue one, the blue points. It could be that it's the more recent one, or maybe some other setting that I wasn't aware of. But you want to turn off the one that you saved so that you're only looking at the new one. All right, so that 870 is now gone, and this is what the data set maps to graphically. So then I'm going to go to, it's not going to automatically recompute the regression. So you go back in, regression, linear, plots the line, go back in, a lot of keystrokes, but now I have y hat is equal to 22.293 plus 1.591x. The r squared value you can get from here, but they've been asking for the r value, so I'm just going to grab that from the stat menu. So r is 0.601. So the outlier without influence, yeah, it had a change in the correlation coefficient, and it had a change in the linear regression equation, but if you compare the slope with that point in compared to the slope without that point in, not much of a change. All right, you might feel like there's a substantial change in the r value, but that's kind of trickier to really call, I guess. And the reality is, the more points you remove from a data set, the more correlation there's going to be between the points. Like if you removed all but 2 points, yeah, you can get a line that fits that perfectly. Right? All you need are 2 points to draw a line, so that would be perfect fit. Right? So we have a slight change in slope. For the r, you could say moderate change, more change, however you want to do it. But I wouldn't say a significant change because I don't know what to compare it to yet, right? So I'll say a moderate change in correlation. All right, so now what I need to do is put back the 870 and remove the 2040 and do the same thing. So obviously this is a process. It takes time. All right, go back to the original data set. Now I can just overwrite, right? Because I want the 2040 to go away, but I want to bring back the 870. So I just take the 20 and replace it with an 8, and the 40 and replace it with a 70. Again, same deal. Graph it. You can see that point off on the side's no longer there. Regress it. All right, go back in, grab the equation, or you can grab the correlation first, and you'll see that it gives you the coefficients in this menu. You know, so you can grab it all here if you don't want to go into that other menu, right? So either way, you just got to remember what the A and B represent. That's the tricky part, right? Right above it, it says the model. So in the beta versions, just be careful which model it says. For this one, I know the slope is the A value and the y-intercept is the B value, so I'll just write that backwards. So 2.3, I'll say 3005. That's my y-intercept. Is that the y-intercept? Feels a little off, but plus 5.0985 with the r value being 0.785. All right. Yeah.
There's supposed to be an X multiplied in the second number in the Y.
Thank you. All right. So we're looking at a massive change in slope here. All right. So I'll say large change. And correlation. Along with that, we got a significant change in the y-intercept, but that doesn't always have as much of an impact on
When you say the change in correlation, are you comparing that to the original?
original. All right, so the correlation went from about 0.4 to about 0.8. All right, that's a significant change. You went from, I mean, even if you're using the made-up table that I gave you, if you're using that, it's like you went from like slight correlation to strong correlation, right? And also graphically, you could just see the fit, right? It looks like it's a much better fit. But then when it comes to the residual plot, which we'll pick up with tomorrow, you always go back to the original graph, all right? Or the original data set, the original graph to come up with a residual plot, all right? So very important. You don't work off of the outliers removed, all right? And then we'll take care of the rest after that. So more on this tomorrow.